Want to make more designs?
Yes.
Okay, but let's take a look at the table first. Let's review. We have here addition table modulo 12. Last time, when we discussed associativity, commutativity, identity, and inverse, I heard somebody mentioning the word group. Who was it? I think he was trying to relate it to his lesson in another subject, which is abstract algebra. Yes, is that correct? Okay. Our set Z12 together with the operation addition modulo 12 forms a group. Why? Because we're talking about a non-empty set, right? So it has the elements 0 to 11. And we are talking also about a binary operation. Remember, we only add 2 elements at a time. And is our binary operation closed? Meaning, if you add any 2 are the sums part of the set, look at this one. Are all the entries here part of the set that contains 0 to 11?
Yes.
Okay, so our operation here is closed. And we have discovered that it is associative and an identity element exists. But what was the identity that we found out? What's the identity? Okay, 0 is the identity element. And did each of the element have an inverse?
Yes.
Okay, therefore, this is a group. It's actually a commutative group. Okay. The question now is Z12 under multiplication modulo 12 also a group? Let's see. This is the table for multiplication modulo 12. Let's check if the properties exist also. Is it commutative? Is it commutative? How do we check for commutativity again? We take any 2 arbitrary elements. So A and B, so is A times B equal to B times A? Actually, there's a simpler way for checking whether a table is commutative or not. What do we need to do? All we need to do is highlight the diagonals and check if the entries are symmetric with respect to this diagonal. Take a look at this. This is 6 times 4. Is it equal to 4 times 6? Yes. They're both 0. And notice the cells, they are symmetric with respect to the diagonal. How about another pair? This is 11 times 2. Is it equal to 2 times 11?
Yes.
Okay, are they symmetric with respect to the diagonal?
Yes.
Actually, for all pairs of elements in the set, you will find that they are symmetric with respect to this diagonal. So this table exhibits commutativity. How about associativity? Is this table associative? Can you give me 3 values from the table? 3 values, 3 elements. Give me 3 elements. Anyone? Yes, Kimberly?
2, 8, and 10.
Okay, let's see. Is 2 times the quantity 8 times 10 equal to the quantity 2 times 8 times 10? Okay, let's see. On the left side, what is 8 times 10? From the table, you get 8. All right. And what is 2 times 8? You'll get 4. Will we get 4 on the other side also? Let's see. What's 2 times 8 from the table? 4. And what is 4 times 10? 4. So, this particular set exhibits associativity. Actually, since this is finite, you can check for each possible group of elements, and you'll find that Z12 is also associative with respect to multiplication modulo 12. Identity. Do you think an identity element exists for this particular set? If 0 is the identity element for Z12 in addition modulo 12, what do you think is the identity element for addition, for multiplication modulo 12?
It's 1.
Any guess? Is it 1? Let's see. Yes. So from the table, you get the same number when you multiply by 1. Okay? So, the identity exists. How about an inverse? Does each of the element have an inverse? Let's see. What's the inverse of 0? In other words, what will you multiply to 0 to get a 1? None. So 0 doesn't have an inverse. How about 1? What's the inverse of 1? 1. Okay, because 1 times 1 is equal to 1. How about 2? Does 2 have an inverse? Will you get a 1 in this row? No. How about 3? Does 3 have an inverse? Will you get a 1 in this row? No. 4? No. Actually, the only elements that have an inverse are these 4. Okay. 1, 5, 7, and 11. So, is this a group? No. It may be commutative, but it's not a group. Okay. So, actually, if we generalize that, Zn with addition modulo n is a group. But Zn under multiplication modulo n does not form a group. Okay? Now, let's make some designs. We'll be making 2 sets of designs. One for addition and another one for multiplication. All right. Do you remember how to construct your addition table? All right. There's an easy way to construct addition tables. So if we talk about Z5, what would our elements be? 0, 1, 2, 3, 4. So this is addition modulo 5. 0, 1, 2, 3, and 4. Alright. So 0 added to this will give you the same set of numbers. If you add 1, you start with 1. You'll get 2, 3, 4. What's next? Do you see a pattern on how to construct the table? Yes, you start here with 2, 3, 4, 0, 1. Here?
4, 0, 1, 2, 3.
All right. Now let's make circular graphs. Since we are talking about Z5, our modulus is 5. Let's concentrate on this. On this addend. 1. So we have 5, so I have to mark 5 points here. This would be 0, 1, 2, 3, 4. All right. Look at this table. I connect 0 to 1. 0 to 1. Next, I connect 1 to 2. 1 to 2. Next, 2 will be connected to 3. 3 will be connected to 4. And 4 will be connected to 0. So what figure will I form? Okay, it's actually a pentagon. All right. What figure will I get if I use 2 now? Any guess? What would my graph look like this time? So this is 0, 1, 2, 3, and 4. So our modulus is 5, our addend is 2. So we will concentrate on this portion of the table. So to whom shall I connect 0? Okay, 0 will be connected to 2, and then 1 will be connected to 3. And then, 2 will be connected to 4. And then, 3 will be connected to 0. What do you think will be formed? 4 will be connected to 1. So this is the graph for 5, 2. Okay? Alright. Actually, there's a simpler way of doing that. Let me show you another table. This is addition table modulo 7. Alright? Let's do 7, 1. So I have to mark 7 points. 0, 1, 2, 3, 4, 5, 6. So to whom shall I connect 0? Okay. So we're doing 7, 1. Actually, all I need to do is to add 1. So if I start from 0, what is 0 plus 1? Okay. What is 1 plus 1? What is 2 plus 2? What is 3 plus... that's 2 plus 1. Sorry. What's 3 plus 1? 4 plus 1? 5 plus 1?
6.
And 6 plus 1?
0.
Okay. That will be the graph for 7, 1. Okay. How about for 7, 2? So again, we mark off 7 points. 1, 2, 3. Let this be 0, 1, 2, 3, 4, 5, 6. So if this is 7, 2, all I need to do is to add 2. So if I start with 0, I'll just count 1, 2, connect. Here, I'll count 2, 1, 2, connect. Count 2, 1, 2, connect. 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 So this will be our graph for 7, 2. Now, are you ready to make your own graphs?
Yes.
All right. So you work in pairs or threes. I'll be giving you sets of papers to work on.